Hey everyone, just wanted to make a quick video over section 4.8. So this is about L'Hopital's rule. So we talked about it a little bit during the review session, how it can be used. So here I'm going to go a little bit more in detail in this section. So it starts out by giving a little example. It says the direct substitution property that we talked about a while back says that if we have a polynomial rational function with the point a being in the domain of the function, then the limit as x goes to a of f of x is equal to f of a. So it looks at this first part of this example. It says consider the limit as x goes to 2 of x squared minus 4 over x minus 2. It says why can we not use the direct substitution? So it goes back to this thing up here that for the direct substitution property or rule to be applied, a must be in the domain of that function. In this case, x equaling 2 is not in the domain of this function here, right here, because we can't plug in 2 of that function in sense. We can't get an actual output. So part B says rewrite it so that you can actually use it. So all you do is factor the numerator into a difference of squares. So x squared minus 4 can be broken up into x plus 2 and x minus 2. The x minus 2's will cancel out in the numerator and denominator and leave you with x plus 2. So then we say that the limit of this right here is actually just equal to the limit of x plus 2 as x goes to 2. And now 2 is in the domain of this here. So we can actually just plug in 2 to find the limit, and it equals 4. So that's just a little bit behind how we actually start these problems. So we would have plugged 2 into this original equation here. We would have got a form of 0 over 0. So this is what it talks about when we have an indeterminate form down here. So this says an indeterminate form is a limit of the form. The limit is x goes to a of f of x over g of x, where either the limit as x goes to a of f of x is 0, and the limit as x goes to a of g of x is 0, or the limit as x goes to a of f of x is infinity, and the limit as x goes to a of g of x is infinity. So these could also either be negative infinity for either of them. It doesn't matter as long as it goes to one of the infinities. So using that idea, let's get the first example here. It just has you identify the form. So it says each limit below is an indeterminate form. Classify it as 0 over 0 or infinity over infinity. So this first one here, part A, says the limit is x goes to 1 of x, ln of x over x minus 1. So if we try to plug in 1 to this expression here, what we're going to get is ln of 1, which is 0 up here, and then x minus 1, which is 0 down here. So this is a type 0 over 0. Let's move on to the next one. So for part B, it says the limit as x approaches pi over 2 coming from the left of secant of x divided by 1 plus tangent of x. So what I did here was just you plug it into a graphing calculator. If you want to, you just pick something close to pi over 2 that's just a little bit less than it and see what it approaches. So it approaches infinity for both of these. So it's type infinity over infinity. And then part C here, the limit as x approaches infinity of e to the x over x squared. So this one is infinity over infinity. So for each of these different types, 0 over 0 or infinity over infinity, we can find the limit of that expression by using what is called L'Hopital's rule. So it says let f and g be differentiable functions such that the derivative of g evaluated at x is not equal to 0 on an open interval I that contains a. So it says suppose that the limit creates an indeterminate form type 0 over 0 or infinity over infinity. Then the limit as x goes to a of f of x over g of x is the same as the limit as x goes to a of the derivative of f of x divided by the derivative of g of x. So it says if the limit on the right-hand side exists or if it's equal to plus or minus infinity. So let's see how we actually apply this L'Hopital's rule. So for this first simple example here to apply it, we know all three of these are a type 0 over 0 or infinity over infinity because they were. right here in example 4.8.3. So I didn't have to say these were in the indeterminate form, or they possessed an indeterminate form, because we already knew they did in this example. So what we want to do now is use that L'Hopital's rule. So I differentiate the numerator and denominator. Differentiating ln of x gives me 1 over x. Differentiating x minus 1 gives me 1. Now, I know that x equaling 1 is in the domain of 1 over x, so I can just plug in x equals 1 in there, and I get that the limit as x goes to 1 of 1 over x is 1 over 1. So we have 1 over 1 divided by 1, which is obviously just 1. So that's the first one there. And you can verify that if you try to plug the stuff into a table, just plug in values that are approaching 1 on the left and the right, and you'll notice that it gets closer and closer to 1. What about the next? So this one was infinity over infinity. So differentiating the numerator, we have the derivative of secant x is secant x tan x. And then differentiating the denominator, the derivative of tan x is secant squared x. So we can cancel out a secant from here and 1 from here. So this leaves us with the limit as x goes to pi over 2 from the left of tangent divided by secant of x. But now what we can actually do is rewrite both of these trigonometric functions out. So tangent x is sine x over cosine x by definition. And secant x is equal to 1 over cosine x. So now notice that these actual cosine x's go away. And I'm left with the limit as x goes to pi over 2 from the left of sine x. And if I plug in pi over 2 into sine x there, I get 1. So that limit is equal to 1. And then part C, we again know that this is a type infinity over infinity. So we can take the derivative of the numerator and denominator. So if we take the derivative of the numerator, that's e to the x. Take the derivative of the denominator, that's 2 to the x. Let x go to infinity. Then up in the top, we have infinity. And also in the bottom, we have infinity. So we have, again, type infinity over infinity here. So what we want to do is apply L'Hopital's rule again and take the derivative of the numerator and the denominator. So the derivative of e to the x is, again, e to the x. The derivative of 2x is 2. Now we let x go to infinity, and we still have that it actually goes to infinity. So that is okay. So the limit existed, technically. It went to infinity. So those are how we find limits using L'Hopital's rule. This next one here, it requires a couple more steps. So it says show that the limit as x goes to 0 of tangent x minus x over x cubed is 1/3. So first thing I did was I said, does this have an indeterminate form? So all I did was I plugged in 0, and yes, it has an indeterminate form of 0 over 0. So since it has an indeterminate form, I can apply L'Hopital's rule in the first step. So all I do is differentiate the numerator first. So the derivative of tangent x is secant squared x. The derivative of minus x is minus 1. And the derivative of x cubed is 3x squared. Now, plug in 0 for x in the numerator and the denominator. And again, we have 0 over 0. So again, we have an indeterminate form. So what we can do is apply L'Hopital's rule again and differentiate the numerator and denominator. Doing that, the derivative of secant squared x minus 1 is secant squared x tan x. And the derivative of 3x squared is 6x. So now plug in 0 again. In the numerator, we have 0. The denominator, we have 0. So we have a type 0 over 0 still. Now, so we use L'Hopital's rule again. Differentiate the numerator and the denominator. Differentiating the numerator gives us minus 4 secant squared x plus 6 secant to the 4th x over 6. So now we just plug in x as 0 to the numerator, and we get minus 4 plus 6 gives us a 2. And in the denominator, we have 6. So 2/6 can be simplified to 1/3. So therefore, we have showed that the limit as x goes to 0 of tan x minus x over x cubed is equal to, or as it has asked us to do. So now this, let's go through the pre-class practice problems real quick. So it says compute these limits. You may or may not need L'Hopital's rule. So the first one says the limit is x goes to minus 2 of x cubed plus 8 over x plus 2. So if I plug in minus 2 in for x into the numerator and denominator, I get 0 for both of them. So it has an indeterminate form of 0 over 0, and I can't apply L'Hopital's rule. So differentiating the numerator, we have 3x squared. Differentiating the denominator, we have 1. So this means we actually have the limit as x goes to minus 2 of 3x squared. And then plugging in minus 2 in for x, we have 3 times 4, which is 12. So that one's a pretty simple one because the denominator, when I took the derivative, was just 1. Let's move on to the next part. So it says the limit as x goes to pi over 2 from the right-hand side of cosine x over 1 minus sine x. So if I plug in pi over 2 for both of those values of x, I get 0 over 0. So I have an indeterminate form, so I can apply L'Hopital's rule. So differentiating the numerator, the derivative of cosine x is minus sine x. And then differentiating the denominator, the derivative of minus sine x is minus cosine x. So this is actually just the derivative of, not the derivative, but minus sine x over minus cosine x is just tangent x. So what I'm doing here is actually taking the limit as x goes to pi over 2 from the right-hand side of tan x. And if you look at the graph of that, it actually goes to minus infinity. Then part C, this one is one where you don't have to use L'Hopital's rule, because if I plug in pi, then all I get is 0 over 2. So there's no need for L'Hopital's rule. The limit is just 0. Then part D, it says the limit as u goes to infinity of e to the u over 10 divided by u cubed. So letting u go to infinity, both the numerator and denominator go to infinity. So we have a type infinity over infinity. So we can use L'Hopital's rule. So differentiating the numerator first, we have to use the chain rule. So it's 1/10 times e to the u over 10. And then in the denominator, we have the derivative of u cubed is 3u squared. Then letting u go into infinity, we still have infinity over infinity, so we need to apply L'Hopital's rule again and differentiate the numerator and denominator. Differentiating the numerator leads to 1 over 100 e to the u over 10. Differentiating the denominator leads to 6u. Again, let u go to infinity. We still have in type infinity over infinity. And we can differentiate. Again, differentiating the numerator gives us 1 over 1,000 times e to the u over 10, then divided by 6. Now let u go to infinity. The numerator goes to infinity. The denominator stays as 6, so the limit is infinity. So that was when we have an indeterminate form of type 0 over 0 or infinity over infinity. So there are some other indeterminate forms that we talk about. So the first one is a type 0 times infinity. So this is where we have a limit of the form, the limit as x goes to a of f of x times g of x, where the limit as x goes to a of f of x is 0, and the limit as x goes to a of g of x is infinity, or vice versa. We could say the limit as x goes to a of f of x is infinity, and the limit as x goes to a of g of x is 0. So now how do we handle these indeterminate forms? So what we want to do is try to rewrite this limit of f of x times g of x, where we have the form infinity over infinity, or 0 over 0 when we take the limit. And then once we have that, we can apply L'Hopital's rule, just like how we did in this example here on these problems. So let's look at this first one here. It says, example 4.8.8, find the limit as x goes to 0 from the right of x times ln x. So if I plug in x is 0 into the x portion, that gives me just 0. And then if I let x go to 0 from the right-hand side, ln x goes to minus infinity. So I have something of the form 0 times infinity. In this case, it's minus infinity, but that doesn't matter. So what I want to try to do is get it where I have type infinity over infinity or 0 over 0. So the way that I do this is just instead of writing x here, I write 1 over x here. And then whenever I take the limit as x goes to 0 from the right, I have it approaches negative infinity on the top, positive infinity on the bottom. So therefore, I can use L'Hopital's rule now and differentiate the numerator and the denominator separately and then limit them. So if I take the derivative of ln x, I get 1 over x. If I take the derivative of 1 over x, I get minus 1 over x squared. But this can be simplified into negative x. So and then when I take the limit as x goes to 0 from the right of negative x, I get 0. You can verify this limit by graphing the function in Desmos and see. Now, moving on to the next one. It says evaluate the limit as x goes to infinity of x times sine of pi over x. So again, we have to figure out this is the type that we're looking for. So here, if I let x go to infinity, then x indeed goes to infinity, and sine of pi over x will go to sine of 0, and sine of 0 is 0. So we have a type 0 times infinity, so we need to rewrite this where we have 0 over 0 or infinity over infinity. Take this x here. 0 over 0, and we can apply L'Hopital's rule. Differentiating the numerator, we have minus pi over x squared times cosine of pi over x. And differentiating the denominator, we have minus 1 over x squared. And then we can cancel out these x squareds here. And this leaves us with the limit as x goes to infinity of pi times cosine of pi over x. So now as x goes to infinity, this becomes pi times cosine of 0, and cosine of 0 is 1, so our limit is just pi. And you could verify this on a graph as well. Just graph this function here, and then plug in some very large values of x, and notice that the actual value of the expression goes to 3.14159 as you increase x. So now this one here is one of those show you problems again. Show that the limit as x approaches pi over 2 from the left of cosine x times secant of 5x is 1/5. So here we need to figure out if we have the type that we want, 0 times infinity. So whenever we plug in pi over 2 into cosine x, this gives us 0. And when we plug in pi over 2 coming from the left of secant of 5 over x, it goes to infinity. So what we can do is write secant of 5 over x as 1 over secant of 5x. But 1 over secant of 5x is just cosine of 5x. So then we have the limit as x approaches pi over 2 from the left-hand side of cosine x over cosine of 5x. And if I plug in pi over 2 here, this is cosine of pi over 2 and then cosine of 5 pi over 2. And both of these equal 0. So this implies that, in fact, I guess I didn't finish this one off. So we need to finish this off real quick. So this would be, we need to take the derivative of this, right? So let's take this cosine x. So the derivative of cosine is minus sine x. So the derivative of cosine of 5x is what? 5, and the derivative of cosine of 5 is 5. Now, what do we get whenever we plug that in? So as we go to pi over 2, let's see, let me check real quick. Sorry, I thought I had this one fully solved. I must have erased it whenever I was rewriting them out from the actual answers I have on the overleaf document. So let's see real quick. Where is the mistake? What did I forget to solve fully? Okay, so we are on example 4.8.10. Okay, let's go to it real quick. There we have, oh, I see where I messed up because the derivative of cosine is minus sine. So I forgot to put the minus out there. So this becomes -1 up here whenever we plug in pi over 2. And then down here we have -5 times 1. This should say sine of 5x right here because the chain rule. So this just gives us what we want, 1/5. There we go. And that's how you solve that problem. Sorry for that. All right. So those are where we have type 0 times infinity, that indeterminate form. Now there's another type we can have where we have infinity minus infinity. So this happens when we have the limit as x goes to a of f of x minus g of x, where both the limit as x goes to a of f of x is infinity and the limit as x goes to a of g of x is infinity. So this first one here, we don't really have to do anything. We just have to notice that we can actually simplify this problem by rewriting the difference in terms of the trigonometric functions expanded out. So here it says the limit as x goes to pi over 2, coming from the left of secant x minus tan x. So if we actually graph this and try to find out what these limits are individually, you end up with infinity minus infinity. So what we want to do now is actually rewrite secant x as 1 over cosine x, which we do right here. And then we want to write tangent x as sine x over cosine x. Now we have a common denominator of cosine x, so we can actually just take 1 minus sine x. And then once we do that, we notice that this is a type 0 over 0. So then I can take the derivative of the numerator and the denominator using L'Hopital's rule. When I take the derivative of 1 minus sine x, this is minus cosine x. And when I take the derivative of cosine x, this is minus sine x. So, and then once I let x go to pi over 2, then the numerator goes to 0, the denominator goes to -1, and our limit must go to 0 since we have a 0 in the numerator and non-zero in the denominator. And you can verify this again by looking into Desmos and then plugging in values of x close to pi over 2 coming from the left. So that one we just did by rewriting secant as 1 over cosine and tangent as sine over cosine. This next one here is a little bit more complicated because what we have to do is get a common denominator. So first I verified that this is type infinity over infinity. So we need to try to rewrite this in some way. So what I did was I actually got a common denominator of x minus 1 times ln of x. So what I need to do is actually multiply this piece here by ln of x over ln of x. And if I do that, I'm left with x ln x in the numerator. And then I need to multiply this piece here by x minus 1. And I'm left with x minus 1 right here. So then once I do all of that and simplify this, I'm left with x ln x minus 1 in the top, and then x minus 1 times ln x in the denominator. And as I let x go to 1, I'm left with this here. ln of x goes to 0. This goes to 0 here as well. So I have a 0 in the numerator here. And then here again in the denominator, I have ln of 1, 0. So this is 0 over 0. Now, since it's type 0 over 0, I can take the derivative of the numerator and denominator by L'Hopital's rule. So here, when I take the derivative of this piece here, x times ln of x, it uses the product rule. So I have x times 1 over x plus ln of x minus 1 in the numerator. And in the denominator, I have x times 1 over x plus ln of x minus 1 over x. And when I let x go to infinity in the numerator, I have 1 plus 0 minus 1. And in the denominator, I have 1 plus 0 minus 1. And again, we still have the type 0 over 0 form. So again, we need to apply L'Hopital's rule. The derivative of ln of x is 1 over x. The derivative of ln of x minus 1 over x is 1 over x plus 1 over x squared. And then I can just plug in x as 1 to the numerator and denominator. If I plug in x as 1 to the numerator, it gives me 1. If I plug in x as 1 into the denominator, it gives me 2. So the limit is 1/2. So this is what we did when we had a type infinity minus infinity. We had to get a common denominator to try to get it of the indeterminate form 0 over 0 or infinity over infinity. Then we can apply L'Hopital's rule until we get a limit or we get negative or positive infinity. So there are also 3 other indeterminate forms that we will briefly talk about. So we have types 0 to 0, infinity to 0, and 1 to infinity. So type 0 over 0 is where we have the limit as x goes to a of f of x to the g of x power. We have the limit as x goes to a of f of x is 0. The limit as x goes to a of g of x is infinity. For type infinity to the 0, the limit as x goes to a of f of x had to be infinity, and the limit as x goes to a of g of x has to be 0. And finally, for type 1 to the infinity, this happens if the limit as x goes to a of f of x is 1, and the limit as x goes to a of g of x is infinity. So then, just like how we had up here, how do we want to do this? We want to rewrite it some way we can have it of the form infinity over infinity or 0 over 0. So this one here, since we have to some power, what we want to do is actually take the natural logarithm. So here's how we do this. We want to take the original function, f of x to the g of x, and let y equal f of x to the g of x, and take the natural log of both sides. And if we do that, we get the natural log of y equals g of x times ln of f of x. And then when we do that, we can get an indeterminate form of 0 times infinity, rewrite the expression just like how we did earlier to get a type 0 over 0 or infinity over infinity. And once we have that, we can apply L'Hopital's rule just like how we've done on the rest of the exercises. So let's look at this one here. So this is compute the limit as x goes to 0 from the right of 1 minus 2 sine x to the cotangent x power. So if I do that, the limit as x goes to 0 from the right of 1 minus 2 sine 2x is 1, and the limit as x goes to 0 from the right of cotangent x is infinity. So here I have 1 to the infinity. So what I want to do is start off by saying let y equal 1 minus sine 2x to the cotangent x power, and I want to take the natural log of both sides. If I do that, that brings the cotangent x out front, and the ln of 1 minus 2 sine x right here. And we can take the limit of this. So cotangent x, remember, is just 1 over tangent. So what I did was I rewrote that here where I have 1 over tangent, so tangent in the denominator, times ln of 1 minus 2x, or 1 minus sine 2x, excuse me. And when we do that, we let x go to 0, and the numerator goes to 0, the denominator goes to 0. So here we have a type 0 over 0, and we can apply L'Hopital's rule by differentiating the numerator and denominator. When we differentiate the numerator, we get minus 2 cosine 2x divided by 1 minus sine 2x. And then when we differentiate tangent x, we get secant squared x down here. Now we let x go to 0 from the right, and then up in the numerator, we have it goes to negative 2 over 1, and the denominator, we have it goes to 1. So the overall limit is negative 2. But remember, what we were actually looking at is taking the natural log of y. So this says that the limit as x goes to 0 from the right of ln of y is minus 2. So we want the actual original limit of y as x goes to 0 from the right. So this is actually equal to, exponentiating both sides, we have e to the minus 2. So this actually implies that our original limit that we wanted, the limit as x goes to 0 from the right of 1 minus sine 2x to the cotangent x power, is actually e to the minus 2. So that's the first one there. We had a type 1 to the infinity. Now let's move on to the next one. So it says, find the limit as x goes to 0 from the right of x to the x power. So as I go to 0, this is a 0 to the 0 type. So again, I let y equal x to the x, take the natural log of both sides, then ln of y is equal to x times ln of x. And what I want to do now is see that this is a type 0 times infinity. So I need to rewrite this in some way. So again, what we did was we wrote x as 1 over x in the denominator. Then we notice that as I limit x to 0 from the right-hand side, this goes to minus infinity over infinity. So we can apply L'Hopital's rule. So the derivative of y equals 0, and so x right. So x is right. Again, we have that the limit of x is 0 to the minus y. So our limit as x goes to 0, the right-hand side of x dx is so that's how we form and then apply a L'Hopital's rule. So now these next couple ones here, it just says find the limits. It doesn't specify all the types. So let's look at the part A. It says the limit as x goes to infinity of ln of x squared over x. So the limit of ln of x squared as x goes to infinity is infinity. The limit as x goes to infinity of x is infinity. So I have a type infinity over infinity. So I can take the derivative of the numerator and the denominator. The derivative of ln of x squared is 2 ln of x times 1 over x. The derivative of x is 1. So I have the limit as x goes to infinity of 2 ln of x over x. And again, as x goes to infinity, this is infinity over infinity. So then differentiating again, I have the derivative of 2 ln x is 2 times 1 over x. And the derivative of x is just 1. So this is just the limit as x goes to infinity of 2 times 1 over x. But that actually goes to 0 because the limit of 1 over x goes to 0 as the limit as x goes to infinity of 1 over x is 0. So that implies that the limit as x goes to infinity of ln of x squared over x is 0. The next one, part B, I said skip this exercise. That one's a little too difficult. Now the next one here, we have a type infinity minus infinity. So what did I do earlier on a problem like this? I pretty much cross multiplied to get a common denominator. So that's what I'm going to do here again. So here I need a common denominator of x times e to the x minus 1. So I have to multiply this here by e to the x minus 1 over e to the x minus 1. Here I need to multiply by x over x. When I do that, I end up with the limit as x goes to 0 from the right of e to the x minus 1 minus x over x times e to the x minus 1. Letting x go to 0, I have a type 0 over 0 here. So I can apply L'Hopital's rule. The derivative of e to the x minus 1 is e to the x minus 1. And the derivative of x e to the x minus x involves the product rule for this piece here. When I apply the product rule for that, I get x e to the x plus e to the x. And then when I take the derivative of minus x, I get minus 1. So, and then I let x go to 0. And again, I have type 0 over 0. So I apply L'Hopital's rule again. The derivative of e to the x minus 1 is e to the x. The derivative of x e to the x plus e to the x is x e to the x plus e to the x plus e to the x. Now I let x go to 0. E to the x goes to 1. And then the denominator goes to 1 plus 1 or 2. So that implies that the limit as x goes to 0 from the right of 1 over x minus 1 over e to the x minus 1 is 1/2. So this one here, we just look at the limit as x goes to 0 coming from the right of each individual piece, and we notice that this actually goes to infinity minus 0 which is not an indeterminate form. The answer is just infinity. These next two exercises you can skip. These ones are a little more difficult. Okay, and then the last couple of ones that I'm going to go over. So it says the equation of the tangent line to f of x at the point 2, 0 is 1.5x minus 3, and the equation of the tangent line to g of x at 2, 0 is 2 minus x. Find the limit as x goes to 0 of f of x minus g of x. So what I did here is notice that the limit as x goes to 0 of f of x over g of x. Here I have the value of each of these. At x equals 2, g of x is 0, and at x equals 2, f of x is 0. So we have a type 0 over 0. So we can say that the limit as x goes to 2 of f of x over g of x is the same as the limit as x goes to 2 of the derivative of f of x over the derivative of g of x. But as x goes to 2, this is actually f prime of 2 over g prime of 2. And since these are tangent lines, we know what the slopes are. So we know what the derivatives are. So here, the derivative of f at 2 is 1.5. And here, the derivative of g at 2 is negative 1. So we have 1.5 over negative 1, or negative 1.5. So that implies that the limit as x goes to 2 of f of x over g of x is 1.5. So that one's a problem you wouldn't expect to need to use L'Hopital's rule on, but it's kind of nifty how we used it. Okay, and then this last one we're going to go over here. It says if f prime is continuous, f of 2 is 0, and f prime of 2 is 7, then find the limit as x goes to 0 of f of 2 plus 3x plus f of 2 plus 5x over x. So what I did here was I wrote the limit as x goes to 0 of this. As x goes to 0, this becomes f of 2 plus f of 2 over 0, and this is a type 0 over 0. So what I now need to do is take the derivative of the numerator and the denominator. When I take the derivative of f of 2 plus 3x, this ends up being 3 times f prime of 2 plus 3x because it uses the chain rule and multiplies by this coefficient of x here. And the same thing here. Here was a coefficient of 5, so that 5 comes out front, and I'm multiplying by the derivative evaluated at the same entropy, so 2 plus 5x on that second term. Now, the limit as x goes to 0 of this becomes the limit of x going to 0 of f prime of 2 plus 3x ends up being f prime of 2. Similarly here, this is also f prime of 2. So I have 3 f prime of 2 plus 5 g prime of 2. So that's 8 f prime of 2. I apologize, I said g prime of 2 right here, but this should have been f prime again. So this ends up being 8 f prime of 2, and we know that f prime of 2 is 7, so this is 8 times 7, or 56. So, and then the last one on here before the after class practice, just skip this question. That one's a little bit more difficult as well. But that is all for section 4.8 for this one. I will post this video, and then I will create your test and practice test here pretty shortly, and those will be up on Moodle. And we will go over that practice test before the test on Monday. Other than that, I don't have anything else. Y'all have a good night and good luck studying.